function for a particle, one particle now. Psi of x. And now let's rotate our frame of reference. Or, better yet, rotate the particle. I'm only interested in the spin right now. So there's a wave function of the particle. It might depend both on position and spins. Yeah, so we can put some spin in, yeah? It depends on whatever it depends on, but in particular it depends on the spin. And now we rotate by some angle. What happens when you rotate a state with a given angular momentum by an angle? Well, an idea? About any axis, whatever. An exterior axis. Right, exterior. The particle could be located. The particle could be located at the origin. So this is such a four-level angular momentum. No, it's whatever angular momentum it has. Everything. Right. Everything, including the spin rotation. We don't know what the spin is. Spin, no. It could be, yes, it could be rotation about the z-axis. Remember, the spin doesn't have to be along the z-axis. It could be along the x-axis, it could be along the y-axis, it could be along any axis.
So the axis of
yes, if its angular momentum is pointing in some direction and you rotate about some other axis, the angular momentum could rotate about that axis. But by the time, here's the angular momentum, here's the axis we're rotating about, and we rotate. But by the time we come back by 2 pi, we come back to the same place. So you might expect that if you rotate the wave function, remember rotation,
university.
Harmonic oscillator. Let's just very briefly review the harmonic oscillator because it's going to come up time and time again in what happens from here on in. As I said, harmonic oscillators are ubiquitous. They're all over the place. Anytime you have a system which has an equilibrium state, it could be classical or it could be quantum mechanical, but classical in particular, if it has an equilibrium state and you displace it from equilibrium, generally speaking, it will oscillate. It may oscillate with more than one frequency. For example, a violin string can oscillate in the fundamental frequency. It can in the first harmonic, the second harmonic, and if you pluck it in odd ways, you can make some nasty noises, as I'm sure that Art knows. Done it many times. The nastiness because of multiple overtones clashing with each other. Well, that's probably not quite right, but you know what I mean. All right, but nevertheless, the oscillations of a violin string are a collection of oscillators of different frequency. But more important to us are the oscillators which comprise the oscillations of the electromagnetic field and other fields. We're going to come to that, and we're going to do a little bit of quantum electrodynamics, just a little bit. But basically, if you have radiation, for example, in a cavity or in a waveguide or something like that, then the radiation, the electric and magnetic fields oscillate with definite frequencies. Again, what would be the equilibrium configuration of the radiation field? I should start with something which has an equilibrium configuration. What is the equilibrium configuration of the electromagnetic field? The answer is no electromagnetic field. The vacuum, empty space with no electromagnetic oscillations in it. No electromagnetic oscillations, in other words, just empty space with no electric and magnetic fields, is the equilibrium position of the electric and magnetic fields, if you like. If you give the system a knock by, for example, sending in some microwaves or something, the system will start to oscillate, and like the violin string, it can oscillate in all of its various frequencies, and those oscillations are called photons. Or that's not quite right. The oscillations are describe collections of photons, and we'll come to that, but not tonight. Okay, so harmonic oscillators are terribly important in many ways. Incidentally, sound waves are also oscillations. A sound wave moving through a crystal is, again, a collection of oscillations. You can think of it wrongly as each crystal oscillating independently of every other each atom oscillating independently of every other atom. But that's not really the way it works. Each atom exerts a force on the other atom, and so when you displace one, it gives a knock to the next one, and waves go through the crystal. The waves, again, are described by harmonic oscillators, and the quanta of the oscillations are not called photons, they're called phonons, for example. So these are things we're going to study, but to prepare ourselves for that, we studied a bit the harmonic oscillator, and I want to expand on it a bit, remind you what the rules are. We started with the harmonic oscillator with a Hamiltonian, which I wrote as p squared over twice the mass, and I set the mass equal to 1 just to make my life simple. You can go back and do it with a mass not equal to 1. I believe in our book art we do it with a general mass, or we do it with, okay, so it's done with general mass. And then plus omega squared, that's the spring constant, but it also happens that omega is the frequency of the oscillator, x squared over 2. And we constructed creation and annihilation operators, A plus or minus, which happen to have been momentum plus I omega x. Now, notice, not finished yet, but notice classically, if I were to take, this is plus or minus, if I were to take the two operators, A plus and A minus, and multiply them together, and then divide by 2, I would construct the Hamiltonian. All right, so we'll come back to that in a minute, but in order to be consistent with the notations that are ancient, we'll put a square root of 2 omega here. And those are the A pluses or minus, and if you work out classically or quantum mechanically the Hamiltonian in terms of A plus or minus, here's what you find. Oh, one more quantity. One more quantity is called N. N is equal to A plus, A minus. As simple as that. And the last time we proved that the spectrum of eigenvalues of N were just the integers starting at 0. We showed that A plus and minus were raising and lowering operators, which raised and lowered the eigenvalues of N. So this is an operator whose eigenvalues are 1, 0, start with 0, no negative ones, 0, 1, 2, 3, dot, dot, dot. And finally, not finally, but moreover, the Hamiltonian is equal to omega. Now, I have left out h bar. I'm going to leave it out, but then I'm just going to show you where it goes. If we leave out h bar, the Hamiltonian is just omega times n. Now where does that come from? If you multiply a plus times a minus, clearly you get something which looks like this. There's a 2 downstairs, that's this 2, and there's an omega